been the source of debate ever since Einstein introduced it in 1917. Einstein produced the cosmological constant because he wanted to have a static space-time model, a static universe. Why did he want a static universe? Well, in 1917, everybody knew that the universe was static. It was unchanging. Okay, all the greatest physicists of the time knew in 1917 the universe was static. When Einstein realized, due to the evidence and other people's work, that the universe was expanding, he said, throw it out, we should not have the cosmological constant. From time to time, it has kept coming back, and as we will see towards the end of this lecture series, today there is evidence that there is a cosmological constant. It's not a big one, it's a small one, but that there is nevertheless a cosmological constant. So if you want to do cosmology today, you must allow for the possible existence of a cosmological constant. Okay, now, the crucial further point is that we need equations of state for our matter. Because the way the universe behaves depends on the equations of state. And to have a stress tensor by itself doesn't tell you very much. You need to know how the matter is behaving. Is it pressure-free matter? Is it radiation? Is it a scalar field? Is it an elastic body? Or whatever. So this is the start, the grounding point for all of this, is that we have got, in a cosmology, we're going to be dealing with gravity, which means general relativity, and you are supposed to have all done courses in general relativity. We have a space-time. We have a metric tensor which tells you time-like clock measurements, space-like distances, and null, the speed of light. That determines the connection, which determines geodesics, which occurs parallel along themselves. That's their geometrical characterization. Physically, they mean motion under gravity and inertia alone. So, for instance, the Earth moving around the Sun, the Moon around the Earth, or the galaxy in the cosmos itself all move on geodesics. A geodesic is parallel along itself. This is the covariant derivative of the tangent vector in the direction x. And light rays move on geodesics. This is the equation which determines the space-time curvature and hence determines the space-time metric. And one of the great things, the amazing things that general relativity did was to come to this realization. Until Einstein, the metric tensor, it wasn't expressed in this way, but essentially until Einstein it was assumed the metric tensor was a constant, it couldn't be a function, and that it was fixed, and it was fixed in some sense non-physically. The huge thing Einstein did was to say, no, the metric tensor is determined by the field equations. That means geometry is part of physics. That's a really amazing thing which Einstein said when he introduced the field equations. He was saying the amount of matter in the universe determines the curvature of space-time as expressed by the Ricci tensor and its contraction, the Ricci scalar. And that then is the way that matter determines curvature and so determines the metric. So geometry was brought into physics by Einstein's great discovery there. Okay, now, in cosmology, this was a very, very brief summary of general relativity, which I have to assume that you know because we don't have time to deal with that as well. In cosmology, there is one extra feature which is very puzzling when you first realize what it is. And the extra feature is that there is a preferred fall velocity in the universe. Now, this is very puzzling because you're told in general relativity that there isn't a preferred fall velocity. In some sense, the whole point of it in using tensors is that there is no preferred fall velocity. Now we're told there is a preferred fall velocity. What we've got here is a classic case of a broken symmetry in physics, and you'll be hearing more about that from Professor Z. The field equations have the symmetry that any coordinate system is equal to any other coordinate system. That's general. But when you come to specific solutions, there are indeed preferred fall velocities. And that preferred fall velocity will be UA. It's a unit time-like vector. In other words, its magnitude is -1. So in the universe, represented like that, there are preferred motions of matter in the universe with a fall velocity vector field UA, and it is a major feature of the cosmos that all velocities are not equivalent. There are preferred velocities. How do you measure that preferred velocity? Well, it represents the average motion of matter. And as soon as you have matter, you can ask what is average motion. So you can form a big box around us. You can have a box big enough to include our galaxy, the Virgo cluster, the Coma cluster, and you measure the masses and velocities and you work out an average velocity. And so that's, if we do it carefully enough, that's a well-defined number, a well-defined vector, and that's the average motion. Nowadays, it is determined in a very, very precise manner indeed from the cosmic background radiation, CBR, cosmic background radiation, which we will be talking about at length, the 3-degree Kelvin black body radiation, which is the remnants of the hot Big Bang phase of the universe. The Nobel Prize for the work done in 1965, Penzias and Wilson, the discovery of the cosmic background radiation, black body radiation at 3 degrees Kelvin. And the point about this, it is 3 degrees, well, it's 2.75 actually. We'd say 3 degrees, it's 2.75 degrees. It is isotropic to an incredible accuracy, but at 1 part in 1,000, delta T over T, at 1 part in 1,000 is non-zero, and that is because of our motion of our galaxy relative to the cosmos, or relative to the background radiation. And if you measure that microwave background at 1 part in 1,000, the sky is hotter in one direction in the sky than the other. Now, the way we understand that is that this is because of our motion at about 300 kilometers per second. We are moving at 300 kilometers a second relative to the background radiation in the universe. And when you take out that motion, get rid of that motion, then once you've taken that out, then take it out, subtract that motion, in other words, change your reference frame to one where you take out that, then delta T over T is of the order 10 to the minus 5, an incredible accuracy, and one of the most important figures in present-day cosmology is the fact that the temperature of the microwave background is isotropic to 1 part in 10 to the 5th once you've taken out the dipolar, which is 1 part in 1,000. And so the way that this is understood today is that we are moving relative to the microwave background at a speed of about 300 kilometers a second, and if you take that out, you get left with the isotropic 1 part in 10 to the 5th. Well, that's something I'll talk about later, but for the moment, this is the important part. What this is determining us, it's determining a rest frame for the universe. And it's determined by the radiation coming from the hot Big Bang at the time of decoupling of matter and radiation. So there is a preferred motion, and it's very accurately determined. It's accurately determined to a few kilometers a second. So what we've got in cosmology, we've got all the apparatus of general relativity, which I've very, very briefly summarized here. But in addition to that, there is a preferred motion. And we talk about people moving with that preferred motion as fundamental observers. You're a fundamental observer if you're moving at that 4 velocity. On this planet, we are not quite fundamental observers. We are moving at this speed relative to the universe. Okay, now, I don't have time to go into a lot of the calculational details, so I'm going to immediately go on from this and talk about the second main point about the universe. This was just my little introduction to general relativity and to the single most important feature of cosmology, this preferred 4 velocity. What this means is we will always work out what happens relative to this preferred 4 velocity. Okay, now, the symmetry and the geometry of the universe are now the next points. What can we think about its symmetries and about its geometry? Okay, now, it is isotropic, the universe is isotropic about us to very high accuracy. We've just seen for the microwave background, it's 1 part in 10 to the 5th, an incredible accuracy. Now, since cosmology seriously started in about 1917, roughly then, cosmologists have been looking in all directions to see if there is anything different about the universe. It's not just the microwave background radiation, all observations are isotropic if averaged over a large enough angular distance scale. Now, if you look at the night sky from Sutherland, you will see the band of the Milky Way covering the sky. So you say, wow, that's not isotropic. Actually, if you look out this window, you see all these buildings. That's not isotropic either. Isotropic means the same in all directions. Same in all directions. So look on a slightly larger scale. Look at the scale of the local cluster of galaxies. Well, that's not isotropic either. Look on a slightly bigger scale. You get the Virgo cluster and all of those. It's still not isotropic. The claim is, if you look on a bigger scale, and Professor Farrell can tell you a lot about this, he will be talking to you later on, average on a large enough scale, something like 200 megaparsecs, something like that. From that scale up, not below, but from that scale up, everything looks the same. Once you've hit that scale, we see, as we look in different directions of the sky, we don't see anything special. We have got no point in the sky which we say is the center of the universe. So if someone says to you, wow, where is the center of the universe? And the answer is the universe does not have a center, because we haven't seen anywhere which is very, very different from anywhere else. Now, these are the observations we make, and what we now do to make progress in cosmology, we make what is called a Copernican assumption. And the Copernican assumption is, well, in the old days we would have said we're not at the center of the universe. Nowadays we phrase it usually to say we are typical. We have no reason to believe that we are different from any other observers. In other words, if you went over to the Virgo cluster and look around, you'd also see a pretty much isotropic sky. And so if we are typical. If you put this together with that, what we deduce, putting together the isotropy and the idea we're not typical, is all observers will see isotropy to very high accuracy, and it is then a mathematical theorem. It is then a mathematical theorem that the universe is spatially homogeneous. It's in a mathematical theorem that the universe is spatially homogeneous, and this is what Walker proved for us. In fact, was this mathematical theorem. So the argument is as follows. We look around on a large enough scale, and you see radio galaxies, you see quasi-stellar objects, you see X-ray sources, you see all of those things. If you look on a large enough scale, you see the same kind of thing in every direction in the sky that you look. So it is isotropic about us. In particular, the microwave background is isotropic to an extremely high accuracy. So what we say to ourselves is, look, there are basically two possibilities. The one possibility is that we are at the center of the universe and everything is made in concentric shells around us. Now that's a possibility. It is possible we are at the center of the universe, and the reason for the isotropy is that everything is built in concentric cells about us. That's possibility A. Center of the universe. Okay, now, this was what everybody believed until about 100 years ago. Everybody believed we were at the center of the universe until 100 years ago. Nowadays, we believe we are typical, not at the center of the universe. If we're typical, then everybody sees things isotropic, and you can actually see the way the proof works in the following way. If both A sees it isotropic and B sees it isotropic, then for A, let us suppose there are shells of density varying with distance going out. But for B, the same argument will hold. So for B, there are also